this is Ken Willis of Cadence Design Systems. Welcome to Sigrity Tech Tips. Today we bring you another installment of how to build and verify your multi-gigabit serial link to meet industry compliance standards. Our video today will show you how to perform analysis of serial link channels using PAM3 and PAM4 signaling. This will be critical if you're involved in designs with automotive Ethernet, which uses PAM3 signaling, or serial link interfaces such as Optical Internetworking Forum, OIF, or Common Electrical I/O, CEI 3.x interfaces, which use PAM4 signaling. This is an important trend in multi-gigabit serial links, where multi-level PAM signaling is being used to multiply the data rate that can be transmitted over a given interconnect channel. You can be confident that Sigrity technology will take you seamlessly into these advanced standards. In today's video, you will see us utilize the Allegro Sigrity SI base and the SystemSI serial link analysis option. To learn more about these products, visit us at www.cadence.com. So now let me turn it over to my colleague, Scott Thomas.
So let's look at NRZ versus PAM encoding. NRZ is what we're used to. It has two valid logic states. So there's a logic high and a logic 0. 1 bit per UI is represented in the SigrityTM channel, and the fundamental frequency is 1/2 the data rate. So we can look at the eye over here. It's the eye that we're commonly seeing, a big wide open eye. In PAM3 encoding, we have 3 valid logic states. So we have a high voltage, a low voltage, and a mid voltage. We implement 1.5 bits per UI transmitted, and the fundamental frequency is 1/3 the data rate. Now if we look at the eye diagram over here, instead of 1 large eye, we have 2 smaller eyes in the vertical space. In PAM4 encoding, we now have 4 valid logic states, the high, the low, and then 2 intermediate states. We transmit 2 bits per UI, and the fundamental frequency is 1/4 of the data rate. And if we look at the eye over here, so instead of 1 or 2 eyes, we now have 3 eyes, and we can see the 4 data states right here. So what are some of the trade-offs when using PAM encoding? One is that the receiver complexity increases. Instead of a simple 1 comparator on NRZ, we now need additional comparators for each of those voltage levels. The clock and data recovery has to also handle multiple zero crossings, so it is more complex on the receiver side. PAM encoding also has a lower signal-to-noise ratio as compared to NRZ, and that is because the vertical eye voltages are lower in PAM than they are in NRZ. However, since the fundamental frequency we're operating at is lower with PAM as compared to NRZ, we tend to be better on the insertion loss curve and have lower loss on a PAM encoded channel than on an NRZ encoded channel. So PAM does have reduced eye openings as compared to NRZ. That means we have lower noise margins and we have lower jitter tolerance. Also, crosstalk tolerance for PAM is less than it is for NRZ. And there is complex trade-offs for power consumption, increased launch amplitude, equalizer complexity, etc. in the receiver and transmitters. So let's now look at a demo of the SystemSI tool with PAM encoding. Here we are in SystemSI. We're going to want to load an example of a PAM4 design. So we're going to create a new workspace. We're going to say it's a serial link analysis, and we're going to want to use the PAM4 template. The default template for a PAM simulation consists of an IBIS AMI transmitter model that supports PAM encoding, a channel, and an IBIS AMI receiver model that is also PAM aware. If we double-click on the transmitter IBIS model, and then select the Stimulus tab at the bottom of the window, we can see the signaling selection is set for PAM4 encoding. If we select the drop-down, we can also see that we support NRZ and PAM3 encoding. We can set the data rate, so in this example, let's set it for 3/8 gigabit per second, and we'll press OK to get back to the canvas. If we double-click on the RX AMI block, we can see a list of AMI parameters that will be passed to the model. We can see that PAM4 is selected in the adapt PAM variable. We can also see that some text files are specified here as well. As the simulation runs, the model will adapt the coefficients in the transmitter and receivers. As these changes occur, they will be written out to these files for later analysis and display. We will see these later on as they are dynamically plotted as the simulation progresses. We can also set the analysis options for the simulation. For example, we can choose to perform a time domain or statistical simulation, change the number of bits in a simulation, or change the bit error rate floor. For our first simulation run, we're going to disable the AMI adaptation and see what happens with the resultant waveform. So we can just right mouse button and click disable, and then we can run our channel simulation. Now, as the simulation runs, you can see that we are dynamically showing you the 2D eye diagram. With the simulation complete, we can see that we have a completely closed eye. So let's go ahead and re-enable the AMI models and see what happens to the simulation. So we can just right mouse button the AMI models, click enable, and then we're going to rerun our channel simulation. Now this time we see a couple of plots occurring down in the lower right-hand corner. The graphs are presenting information about the receiver operation, such as the CTE and DFE adaptation. With the simulation complete, we can now look at the quality of the eyes. Over here we can see the 3D eye density diagram. We're going to rotate it around to get a better view of what is occurring in the 3D eye density. We can also look at a 3D bathtub, so we can get an idea of what happens to the bit error rate in both the voltage and time axes. We also have the ability to look at the 2D results. The first thing we're seeing right here is a composite eye contour of the 3 different eyes in the PAM4 encoding. We can also look at the waveform. So if we zoom in here, let's look at what's happening in the time domain. Here we can see that we have the 4 unique voltage levels. We have a high, a low, and then the 2 intermediate results. Finally, SystemSI produces a summary report that contains the result of the simulation. We're going to have information about the eye width and height, jitter, and bit error rate measurements.
Thank you for watching another edition of Sigrity Tech Tips. For information on products used in today's video, click on the links below or contact your local Cadence sales representative or Cadence channel partner.